Why is there something rather than nothing? How did everything begin? What was there before the beginning? Where did the material come from that created the Big Bang? What happened in the first instance to create that material? Why are we here? When it comes to understanding the universe, trust me, we've barely scratched the surface. These questions I asked above have been circulating in the realms of human curiosity for countless generations, transcending time and spanning cultures. We've been sending different telescopes, like the James Webb and Hubble, to explore the depths of the cosmos. These marvels of engineering have actually done a great job in unraveling some of the universe's secrets, possibly shedding light on a small fraction of its vastness. Day in and day out, we've diligently scanned the skies, capturing breathtaking images of distant galaxies, nebulae, and celestial phenomena, expanding our knowledge of the cosmos with each observation. Through these telescopes, we've witnessed the birth and death of stars, marveled at the intricate dance of galaxies and cosmic collisions, and unraveled the mysteries of black holes. We've measured the redshift of distant galaxies, allowing us to peer back billions of years into the past, offering a glimpse of the universe in its infancy. But with all of these magnificent discoveries, we still have numerous unanswered questions everywhere. Why? When? How? Where? Can we ever answer these questions? Well, you have to keep watching. The last star will slowly cool and fade away. With its passing, the universe will become once more a void, without light or life or meaning. This statement was mentioned by physicist Brian Cox in a BBC series. This is how everything might end. Some other theories suggest that our very own Big Bang, the genesis of our universe, might have originated from a previous incarnation of emptiness, a cold, dark, and empty universe similar to the one awaiting us in the distant future. This is just the first theory. What about theory 2, which suggests there is no first man or woman, no singular event that sparked the universe into existence? Instead, the universe has always been and will always be existing in a state of perpetual existence. According to this theory, the cosmos undergoes an unending series of expansions and contractions, with each cycle seamlessly transitioning into the next. It is an eternal cosmic dance, where the fabric of reality remains constant, unaffected by the passage of time. This theory challenges our conventional notions of a linear timeline and a definitive origin. It suggests that the concept of before and after loses its meaning, as the universe persists in a state of unending existence. It invites us to reimagine the nature of reality itself, where the eternal cosmos encompasses all possibilities. And then, Theory 3 takes us even further, suggesting the existence of infinite universes, each with its own set of physical laws, constants, and conditions. According to this theory, our universe is just one among an infinite ensemble of parallel universes. Each universe within this vast ensemble may have different properties, leading to a staggering array of diverse realities. Every conceivable outcome and configuration exists, encompassing an unimaginable breadth of cosmic landscapes. From universes where the laws of physics are entirely different to those where life takes on forms we can scarcely imagine. Strange, right? The next one, Theory 4, suggests that the reality we perceive as the universe is, in fact, a sophisticated program created by an advanced civilization or a higher intelligence. In this scenario, our entire existence, including the laws of physics, the fundamental particles, and even our own consciousness, is a product of an intricately designed computer program. It proposes that what we perceive as the physical world is a complex virtual construct, akin to some sort of hyper-advanced video game. Supporters of this theory argue that the rapid advancements in technology and computing power, along with our own efforts to create realistic virtual environments, point towards the feasibility of such a universe. They propose that an advanced civilization with incomprehensible computing capabilities could create a simulated reality that is indistinguishable from the real universe. Well, I've given you about 4 theories. If you know the names of these theories, make sure you comment their names below. Let's continue. You see, the universe is very strange. We've got particles popping in and popping out of existence everywhere. There's something, and then pop, nothing. We've got dark matter, a mysterious substance that makes up a significant portion of the universe's mass, but remains invisible to our current methods of observation. It does not emit, absorb, or reflect light, yet its gravitational effects can be observed in galaxies and the large-scale structure of the universe. We've also got dark energy, which seems to be expanding the universe with immense speed. Unlike gravity, which acts as an attractive force, dark energy seems to push galaxies apart, causing the fabric of space itself to stretch. This expansion occurs on such a grand scale that it surpasses the gravitational forces between galaxies, leading to an ever-widening cosmic expanse. And then we have the Big Bang, which tries to explain the origin and evolution of our universe. That the universe as we know it began from an incredibly hot and dense state approximately 13.8 billion years ago, suggesting that all matter, energy, space, and time originated from a singularity, a point of infinite density and temperature. In an extraordinary event, the universe rapidly expanded and continues to expand to this day. It was during this expansion that the fundamental forces and particles that govern the cosmos came into existence. But is it perfect? Did the Big Bang happen inside space, or was the Big Bang the beginning of space itself? Where did it happen, and how did it happen? Why did it happen in the first place? You see, the Big Bang Theory gives us a remarkable glimpse into the birth of our universe, but there are still many unanswered questions. We may have an idea of what happened after the Bang, but what happened before the Bang is where we are left hanging. How could all matter, energy, space, and time be packed into a point of infinite density and temperature? It boggles the mind. Strangely enough, some cosmologists entertain the idea that a previous incarnation of emptiness, a cold, dark, and empty universe, similar to the one awaiting us in the distant future, could have been the source of our very own Big Bang. This may sound confusing, but let me explain what I mean. First off, I want us to look at how the concept of material or physical matter came into existence. When we consider the origins of stable matter composed of atoms or molecules, it becomes clear that such matter did not exist during the initial stages of the Big Bang, nor for hundreds of thousands of years thereafter. The early universe was a hot and dense environment, filled with highly energetic particles that prevented the formation of complex matter. However, as the universe expanded and cooled over time, conditions became favorable for the formation of the first atoms. This process, known as nucleosynthesis, allowed simpler particles to combine and create stable atoms such as hydrogen and helium. But this understanding doesn't address the question of whether something came from nothing. Going further back in time, around 1/10,000th of a second after the Big Bang, the first long-lived matter particles, namely protons and neutrons, emerged. These particles form the building blocks of atomic nuclei. Prior to this crucial moment, there wasn't any material as we commonly understand it, but physics lets us keep on tracing the timeline backward to physical processes which predate any stable matter. This brings us to the fascinating era known as the Grand Unified Epoch. At this stage, we delve into the realm of speculative physics since our current experiments cannot generate enough energy to directly observe the processes that occurred during that time. Nonetheless, there is a plausible hypothesis that the physical world consisted of a swirling mixture of short-lived elementary particles, including quarks, which are the fundamental constituents of protons and neutrons. During this epoch, there existed both matter and its antimatter counterpart in roughly equal amounts. Each matter particle, such as a quark, had its antimatter counterpart, which was almost identical but differed in one aspect. However, whenever matter and antimatter encountered one another, they would instantaneously annihilate, transforming into pure energy. As a result, these particles were constantly being created and destroyed, a vibrant dance of matter and antimatter. But how did these particles come into existence in the first place? According to quantum field theory, even a seemingly empty vacuum, which corresponds to empty space-time, is teeming with dynamic energy fluctuations. These fluctuations have the potential to give rise to particles spontaneously appearing, only to vanish shortly thereafter. At first glance, this might seem like a peculiar mathematical phenomenon rather than something grounded in physical reality. However, the existence of such particles has been observed in numerous experiments, providing tangible evidence of their fleeting existence. The space-time vacuum state is a bustling realm where particles are continuously being created and annihilated, seemingly emerging out of nothing. However, this observation leads us to consider that the quantum vacuum, despite its name, is not an empty void, but rather a dynamic entity in its own right. This notion challenges the idea of getting something from nothing. Suppose we ask the question, where did space-time itself arise from? We find ourselves delving deeper into the distant past, reaching the ancient Planck epoch, a period so early in the universe's history that our best theories of physics break down. This era occurred only 1/10,000,000th of a trillionth, of a trillionth, of a trillionth of a second after the Big Bang. At this point, space and time themselves became subject to quantum fluctuations. Physicists ordinarily work separately with quantum mechanics, which rules the microworld of particles, and with general relativity, which applies on large cosmic scales. But to truly understand the Planck epoch, we need a complete theory of quantum gravity, merging the two. While we have yet to achieve a definitive theory of quantum gravity, scientists have made notable attempts through frameworks such as string theory and loop quantum gravity. Within these approaches, the conventional notions of space and time undergo a transformation. They are perceived as emergent phenomena, analogous to the rippling waves that manifest on the surface of a vast ocean. According to these theories, our familiar experience of space and time arises from underlying quantum processes occurring at a minuscule microscopic level. These processes, operating beyond our intuitive grasp as beings entrenched in the macroscopic world, present intriguing challenges to our understanding. In the Planck epoch, our ordinary understanding of space and time breaks down, so we can't even rely on our ordinary understanding of cause and effect either. Despite this, all candidate theories of quantum gravity describe something physical that was going on in the Planck epoch, some quantum precursor of ordinary space and time. But where did all of that come from? Even if causality no longer applies in any ordinary fashion, it might still be possible to explain one component of the Planck epoch universe in terms of another. Unfortunately, by now even our best physics fails completely to provide answers. Until we make further progress toward a theory of everything, we won't be able to give any definitive answer. The most we can say with confidence at this stage is that physics has so far found no confirmed instances of something arising from nothing. To truly answer the question of how something could arise from nothing, we would need to explain the quantum state of the entire universe at the beginning of the Planck epoch. All attempts to do this remain highly speculative. In 2020, renowned physicist Roger Penrose, a recipient of the Nobel Prize, introduced an intriguing yet controversial concept known as conformal cyclic cosmology to describe a cyclical universe. A cyclical universe is a model of cosmic evolution according to which the universe undergoes endless cycles of expansion and cooling, each beginning with a big bang and ending in a big crunch. Penrose was motivated by a fascinating mathematical relationship between the hot, dense, and small state of the universe during the Big Bang and the cold, expanded, and empty state it is predicted to reach in the distant future. His radical theory proposes that these states become mathematically identical when taken to their extreme limits. This paradoxical notion suggests that the complete absence of matter could potentially give rise to all the matter that exists in our observable universe today. In this perspective, the Big Bang emerges from what can be considered as almost nothing. This notion arises when all the matter within a universe is gradually absorbed by black holes, which eventually dissipate into photons and vanish into a vast void. Thus, the entire universe originates from a state that, when observed from an alternative physical standpoint, closely resembles absolute nothingness. However, even within this apparent nothingness, there exists a particular kind of something. It is still a physical universe, albeit one that is remarkably empty and devoid of traditional matter. How can the very same state be a cold, empty universe from one perspective and a hot, dense universe from another? The answer lies in a complex mathematical procedure called conformal rescaling, a geometrical transformation which in effect alters the size of an object but leaves its shape unchanged. Penrose demonstrated how the cold, dense state and the hot, dense state could be connected through this rescaling process. aligning their space-time shapes while disregarding their sizes. It can be challenging to comprehend how two objects can be considered identical when they have different sizes, but Penrose suggests that size loses its conventional meaning in these extraordinary physical environments. The focus shifts towards understanding the fundamental nature of the spacetimes and the underlying connections between them, transcending the constraints of size as we typically perceive it. In conformal cyclic cosmology, the explanation unfolds in a unique manner, from the old and cold state to the young and hot state. The existence of the hot dense state is attributed to the cold empty state, but this because is not the usual cause and effect relationship we are familiar with, where one event follows another in time. In these extreme states, not only does size lose its significance, but so does time. The cold dense state and the hot dense state exist on different timelines, separated by their distinct temporal geometries. From the perspective of an observer within the cold empty state, it would persist indefinitely in its own timeline. However, the hot dense state that emerges creates a new timeline entirely, with its own distinct properties and evolution. It may help to understand the hot dense state as produced from the cold empty state in some non-causal way. Perhaps we should say that the hot dense state emerges from, or is grounded in, or realized by the cold empty state. These are distinctively metaphysical ideas which have been explored by philosophers of science extensively, especially in the context of quantum gravity, where ordinary cause and effect seem to break down. At the limits of our knowledge, physics and philosophy become hard to disentangle. Conformal cyclic cosmology provides us with intriguing and speculative insights into the origins of our Big Bang. However, even if Penrose's ideas are confirmed by future advancements in cosmology, we may find ourselves confronted with a deeper philosophical inquiry. This inquiry revolves around the origin of physical reality itself and raises the fundamental question of how the entire system of cycles came into existence. Ultimately, we are led to ponder one of the most profound questions in metaphysics. Why is there something rather than nothing? This question delves into the very nature of existence and challenges us to explore the mysteries of our reality at its most fundamental level. But our focus here is on explanations that remain within the realm of physics. There are three broad options to the deeper question of how the cycles began. It could have no physical explanation at all, or there could be endlessly repeating cycles, each a universe in its own right, with the initial quantum state of each universe explained by some feature of the universe before. Or there could be one single cycle, and one single repeating universe, with the beginning of that cycle explained by some feature of its own end. The latter two approaches avoid the need for any uncaused events, and this gives them a distinctive appeal. Nothing would be left unexplained by physics. Penrose envisions a continuous sequence of new cycles, driven in part by his interpretation of quantum theory. In quantum mechanics, a physical system exists in a superposition of multiple states simultaneously and only resolves into a specific state upon measurement. According to Penrose, each cycle involves random quantum events unfolding in unique ways, resulting in variations between cycles. This concept holds promise for experimental physicists, as it suggests the possibility of detecting remnants or anomalies from the previous universe that gave birth to our own. By studying the faint traces in the residual radiation from the Big Bang, observed by satellites like Planck, we may gain insights into the ancient universe that preceded ours. Penrose and his collaborators believe they may have spotted these traces already, attributing patterns in the Planck data to radiation from supermassive black holes in the previous universe. However, their claimed observations have been challenged by other physicists, and the jury remains out. Endless new cycles are key to Penrose's own vision. But there is a natural way to convert conformal cyclic cosmology from a multi-cycle to a one-cycle form. Then physical reality consists of a single cycle around through the Big Bang to a maximally empty state in the far future, and then around again to the very same Big Bang, giving rise to the very same universe all over again. This notion aligns with an alternative understanding of quantum mechanics called the many worlds interpretation. According to this interpretation, when we measure a system in a superposition, the result we observe is not a random selection. Instead, it represents just one possibility that unfolds in our own universe. In the many worlds interpretation, each of the other measurement outcomes plays out in separate parallel universes within a vast multiverse, entirely disconnected from our own. Therefore, no matter how improbable an event may be, if it has a non-zero probability, it occurs in some quantum parallel world. In these other worlds, there are individuals similar to you who have won the lottery, been caught up in unusual typhoons, spontaneously combusted, or even experienced all three events simultaneously. Our Big Bang might be the rebirth of one single quantum multiverse, containing infinitely many different universes all occurring together. According to some theories, parallel universes could leave traces in the data we observe from the cosmos, such as signs of collisions between our universe and others. This idea connects with the concept of many worlds quantum theory, although not everyone agrees, including Penrose. In this view, our Big Bang could mark the beginning of a vast quantum multiverse where countless universes coexist simultaneously. In this multiverse, every possible event and outcome takes place, repeating endlessly in a cycle of existence. It suggests that everything imaginable not only happens once but occurs repeatedly, creating a rich tapestry of infinite universes. Okay, to understand how the universe came from nothing, we need to delve into its nature. Our universe operates in two fundamental ways, which shape the fabric of reality and provide insights into its origins. The first mode is the deterministic nature of the universe. Determinism suggests that every event and outcome in the universe is governed by a set of predetermined conditions and the laws of nature. This viewpoint posits that if we possess complete knowledge of the initial state of the universe and the governing laws, we can predict the future trajectory of events with certainty. Determinism provides a sense of order and predictability, offering a foundation for scientific inquiry and understanding. However, as we explore deeper into the mysteries of the universe, we encounter the second mode of operation, the probabilistic nature of the universe. This aspect, prominently observed in the realm of quantum mechanics, introduces inherent randomness and uncertainty into the fabric of reality. At the subatomic level, particles and their properties exhibit probabilistic behavior, where outcomes are expressed as probabilities rather than definite predictions. This probabilistic nature challenges the strict determinism of classical physics and brings to light the fascinating realm of quantum indeterminacy. The interplay between determinism and probability raises profound questions about the nature of the universe and its origins. How do these two modes coexist? Can determinism fully explain the complex emergence of our universe from nothingness, or does the probabilistic nature of quantum mechanics play a role? Exploring these questions allows us to peer into the fundamental nature of reality itself. Determinism, as we have discussed, proposes that every event and outcome in the universe is predetermined by a set of initial conditions and the laws of nature. In the context of the universe coming from nothing, determinism provides a framework for exploring the sequence of events that could have led to its existence. At the earliest moments of the universe, we imagine a state of absolute nothingness. In this hypothetical scenario, there is no matter, energy, or even space and time as we know them. However, according to determinism, there must have been a specific set of initial conditions that set the stage for the universe's emergence. These initial conditions could involve various factors, such as the properties of the singularity, the values of fundamental constants, or even the existence of additional dimensions beyond our current understanding. The exact nature of these initial conditions is still a subject of intense scientific investigation and speculation. According to determinism, the evolution of the universe is governed by the laws of physics, such as general relativity and quantum mechanics. These laws dictate how matter, energy, and space-time interact and evolve over time. By understanding these laws and the initial conditions that set the stage for the universe's existence, we can trace the sequence of events that led to its formation. As the universe expands, matter and energy undergo various transformations and interactions. Particles emerge, forces come into play, and structures begin to form. Through the interplay of gravity, electromagnetism, and the strong and weak nuclear forces, galaxies, stars, and planets take shape over vast cosmic timescales. Determinism allows us to conceive of this cosmic symphony as a deterministic process, where each stage of the universe's evolution is intricately connected to the preceding conditions and governed by the laws of nature. The properties of matter, the formation of galaxies, and the emergence of life can be seen as the inevitable outcomes of this grand deterministic unfolding. Moreover, determinism offers an explanation for the fine-tuning observed in the universe. The fundamental constants and physical parameters, such as the strength of gravity or the masses of particles, appear to be precisely adjusted to allow the existence of complex structures and life. Determinism posits that these finely tuned values are not mere coincidences, but the result of the deterministic unfolding of the universe from its initial conditions. On the other hand, we have the probabilistic nature of the universe, which introduces a realm of inherent randomness and uncertainty into the fabric of reality. In the realm of quantum mechanics, the probabilistic nature of the universe becomes particularly prominent. At the subatomic level, particles and their properties do not follow strict determinism, but rather exhibit probabilistic behavior. This means that the outcomes of certain measurements or observations are expressed as probabilities, rather than definite predictions. One of the key concepts in quantum mechanics is the wave-particle duality. It suggests that particles, such as electrons or photons, can exhibit both wave-like and particle-like behavior. When it comes to observing the properties of these particles, such as their position or momentum, their behavior becomes inherently uncertain. The famous Heisenberg uncertainty principle captures this fundamental uncertainty. It states that there is a limit to how precisely we can simultaneously know certain pairs of properties, such as position and momentum or energy and time. The more accurately we try to measure one of these properties, the less precisely we can know the other. This inherent uncertainty is not due to limitations in measurement, but is a fundamental characteristic of the probabilistic nature of the universe. The probabilistic nature of quantum mechanics becomes further pronounced through phenomena such as superposition and entanglement. Superposition refers to the ability of particles to exist in multiple states simultaneously until they are observed or measured. This implies that before observation, a particle can be in a state of being in multiple places or having multiple properties at once. Entanglement, on the other hand, refers to the mysterious correlation that can exist between particles, even when they are separated by vast distances. When particles become entangled, their properties become linked, and changes in one particle instantaneously affect the other, regardless of the distance between them. This non-local and seemingly instantaneous connection challenges our intuitions about causality and further highlights the probabilistic nature of the universe. The probabilistic nature of the universe poses intriguing questions about the role of chance and randomness in its emergence. Could it be that the initial conditions that led to the universe coming from nothing were themselves subject to probabilistic fluctuations? Did chance play a role in the precise values of fundamental constants and the emergence of the conditions necessary for the development of life? These questions push us to explore the interplay between determinism and probability in understanding the universe's origins. While determinism provides a framework for tracing the evolution of the universe from its initial conditions, the probabilistic nature suggests that chance and randomness may also play a significant role in shaping the course of events. These two perspectives offer complementary lenses through which we can explore the intricate fabric of reality, yet they often appear as separate strands, awaiting a unifying thread that can weave them together into a comprehensive tapestry. These two perspectives, determinism and probability, seem to occupy separate realms of understanding. Determinism provides order, predictability, and a sense of causality, while probability introduces chance, unpredictability, and the intrinsic fuzziness of reality. They appear as distinct entities, awaiting reconciliation and a unifying framework. The challenge lies in reconciling these seemingly divergent perspectives, bridging the gap between the deterministic and the probabilistic. At the crossroad of these theories, we find ourselves in what physicists call the theory of everything or the final or ultimate theory. The theory of everything represents a profound quest for a unified framework that can encompass both determinism and probability, providing a comprehensive understanding of the universe. It seeks to harmonize the precise order of deterministic laws, such as general relativity, with the inherent randomness and uncertainty of quantum mechanics. This endeavor aims to reveal a deeper synthesis where the deterministic and the probabilistic coexist, enriching our understanding of the nature of reality. In the pursuit of a theory of everything, scientists and theorists explore various avenues, including string theory, loop quantum gravity, and other quantum gravity frameworks. These approaches strive to merge the deterministic laws governing large-scale phenomena with the probabilistic behavior of particles at the quantum level. They seek to uncover the unifying principles that underpin the fabric of the universe, from the majestic dance of galaxies to the subatomic interplay of particles. Yet, the path to a theory of everything remains an ongoing endeavor, filled with challenges and open questions. The intricate nature of quantum gravity, the enigma of space-time, and the puzzle of unifying fundamental forces present complex frontiers that continue to be explored. Nevertheless, the quest for a theory of everything is driven by the recognition that the deterministic and the probabilistic aspects of the universe are not mutually exclusive. They are intertwined threads waiting to be woven into a coherent narrative. Through the unification of these perspectives, we strive to unravel the deepest secrets of existence, to understand how the deterministic laws and the probabilistic nature coalesce, and to grasp the underlying fabric of the cosmos. If the Big Bang Theory is true, how did it lead to all the planets, stars, and galaxies we can see today? Thanks to a series of calculations, observations from telescopes on Earth and probes in space, our best explanation is this. Around 13.8 billion years ago, all the matter in the universe emerged from a single minute point, or singularity, in a violent burst. This expanded at an astonishingly high rate and temperature, doubling in size every 10 to minus 34 seconds, creating space as it rapidly inflated. Gravity and all the other forces were formed within a tiny fraction of a second. The energy changed into particles of matter and antimatter, which largely destroyed each other. But luckily for us, some matter survived. Protons and neutrons started to form within the first second. Within minutes, these protons and neutrons could fuse and form hydrogen and helium nuclei. After 300,000 years, nuclei could finally capture electrons to form atoms, filling the universe with clouds of hydrogen and helium gas. After around 380,000 years, it left behind a bath of photons, the cosmic microwave background that Penzias and Wilson accidentally detected. Within this were tiny ripples of matter that were stretched to enormous sizes during inflation, and in turn, these became the seeds for the galaxies and galactic clusters we see today. Today, when we look out at the universe, the full suite of observations we've collected, even with the known uncertainties taken into account, all point towards a remarkably consistent picture. Our universe is made of matter, obeys the same laws of physics everywhere and at all times. It's governed by general relativity, it's expanding and cooling and gravitating, and it's dominated by dark energy and dark matter, with normal matter, neutrinos, and radiation making up the rest. Today, it's full of galaxies, stars, planets, heavy elements, and intelligent and technologically advanced life in at least one location. These structures weren't always there, but instead arose as a result of cosmic evolution. In a remarkable scientific leap, 20th century scientists were able to reconstruct the timeline for how our universe went from a mostly uniform universe, devoid of complex structure and consisting exclusively of hydrogen and helium, to the structure-rich universe we observe today. If we start from today, we can step backwards in time and ask where any individual structure or component of that structure came from. For each answer we get, we can then ask, okay, but where did that come from? And how did that arise? Going back until we're forced to answer, we don't know, at least not yet. Then, at last, we can contemplate what we have and ask, how did that arise? And is there a way that it could have arisen from nothing? To begin with, the life we have today comes from tiny particles that make up everything around us. These particles are like building blocks, and they join together to make complex molecules, which are the ingredients for life. These building blocks are made of even smaller parts called atoms. The atoms are like the basic elements that make up everything in the universe. But these atoms didn't just appear when the universe began. They needed a long process to form. This process involves stars being born, living their lives, and then dying. When stars die, they create new materials through powerful reactions. These materials are then used to make new stars, and the cycle continues. This cycle is necessary for things like planets and complex chemistry to exist. For the universe to have stars and galaxies like we see today, a few important things had to happen. Gravity had to pull smaller groups of stars and galaxies together to form larger ones. This required having some mass to start with, which gathered more mass due to gravity. To prevent matter from being lost into space during star formation, something called dark matter had to be present in the early stages. The right balance of different types of matter and radiation was needed to create things like the glow left over from the Big Bang and the basic elements. To make galaxies and other structures, there needed to be slight variations in the density of matter, and these variations grew over time because of gravity. The initial imbalances in density, along with the creation of dark matter and normal matter, were essential to make everything we see. So, when we think about whether the universe could come from nothing, these are the important things that we don't fully understand yet. Physics usually treats matter and antimatter equally, meaning reactions create or destroy both in the same amounts. At the universe's start, matter and antimatter could have been made in huge quantities due to its extreme heat and density. But somehow, the universe ended up having more matter than antimatter, even though they should have been equal. There are different ways this could have occurred, although we're not certain which happened. All these ways involve three main things: special conditions where things aren't balanced, which happens as the universe expands and cools; processes that break the usual rules and allow interactions that create more matter than antimatter. The standard model of physics allows for this through something called Sphaleron interactions, a way to create enough of a certain type of violation that helps make more matter than antimatter. The standard model includes these ideas, but they aren't enough by themselves. If you think of a universe with equal matter and antimatter as a universe with nothing, then it seems our universe did create something from nothing, even though we're not entirely sure how it happened. Likewise, there are various ways to create dark matter. We've determined through a lot of testing and research that dark matter can't be made of the particles found in the standard model of physics. Whatever dark matter is, it calls for new physics beyond what we currently know. Different possibilities exist for how it could have formed, such as being made during the early, hot phase of the universe and then not completely disappearing, so it remained stable. Forming during a phase change as the universe expanded and cooled, where big particles come out of nowhere, existing as a different type of neutrino, which could mix with regular neutrinos or be a heavier kind alongside the usual ones, coming about solely due to gravity, creating an extremely heavy particle. Why do we have dark matter today when the rest of the universe seemed to function fine without it in its early stages? There must have been a way to create this thing when it didn't exist before. However, all these possibilities need energy. So the question is, where did all that energy come from? Perhaps according to cosmic inflation, our leading theory of the universe's pre-Big Bang origins, it really did come from nothing. When we picture the very start of the hot Big Bang, we're thinking of something super hot, crowded, and full of energy. Now, when we wonder how this all came about, there are two ways to think about it. First, we can simply say that the universe was born this way. This means the initial conditions were set like this, and we don't have a further explanation. In the world of theoretical physics, we call this approach giving up. Alternatively, we can do what theoretical physicists love to do: come up with a theory to explain those initial conditions. We work to make predictions that are different from what the current accepted theory says, and then we go out to test those predictions. Enter cosmic inflation, which came from this second approach and changed how we see the birth of the universe. Instead of imagining the hot and dense start as an infinitely tiny, infinitely hot point, inflation proposes that before the hot Big Bang, there was a phase where space itself had an incredibly high energy density. This caused the universe to expand extremely quickly during inflation. When inflation ended, that energy turned into matter, antimatter, and radiation, creating what we recognize as the hot Big Bang aftermath. In more detail, this inflation not only makes a universe with the same temperature everywhere and a flat appearance, but also predicts specific kinds of variations in density. When we observed these variations, they matched what inflation predicted. From almost empty space, though it's space full of energy, a natural process has crafted the entire universe we can see today, full of structures. This is the big idea of how we could get a universe from seemingly nothing, although not everyone finds it completely satisfying. For many people, it's hard to imagine a universe without space, time, and the rules of physics. We can think of a place outside space, a moment beyond time, or conditions that aren't bound by physical reality. These thoughts make sense if we consider these aspects as things we'd need to remove to reach a true state of nothingness, at least from a philosophical standpoint. However, there's a difference between philosophical nothingness and a more scientific view of nothingness. There are 4 scientific ways to define nothing, each valid in its own context. A time when something didn't exist, an empty space. Space-time in its emptiest state with the lowest possible energy. Whatever remains when you remove the entire universe and its governing laws. If we use the first 2 definitions, we can say we've started with nothing and created a universe. But if we consider the 3rd definition, it's not so clear. Unfortunately, we lack enough knowledge to say anything about the 4th definition. Without a scientific theory describing what exists beyond the universe and the laws that apply there, the idea of true nothingness lacks a clear physical definition. In the context of physics, it's impossible to make sense of an idea of absolute nothingness. What does it mean to be outside of space and time? And how can space and time sensibly, predictably emerge from a state of non-existence? How can space-time emerge at a particular location or time when there's no definition of location or time without it? Where do the rules governing quanta, the fields and particles both, arise from? This line of thought even assumes that space, time, and the laws of physics themselves weren't eternal, when in fact they may be. Any theorems or proofs to the contrary rely on assumptions whose validity is not soundly established under the conditions which we'd seek to apply them. If you accept a physical definition of nothing, then yes, the universe as we know it very much appears to have arisen from nothing. But if you leave physical constraints behind, then all certainty about our ultimate cosmic origins disappears. Many scientists suggest that the universe might have emerged from nothing, an idea rooted in quantum theory. This notion hinges on the concept that quantum fluctuations could trigger the spontaneous creation of a universe out of nothingness. However, this idea lacked solid support due to the absence of mathematical evidence. Enter Dongshan. He and his team from the Wuhan Institute of Physics and Mathematics. They've made a significant contribution by offering the first mathematical proof that the Big Bang could indeed be a result of quantum fluctuations. Central to this breakthrough are the Wheeler-DeWitt equation and the Heisenberg uncertainty principle. The Wheeler-DeWitt equation marks a significant step in the quest for a theory that encompasses everything. Back in the 1960s, John Wheeler and Bryce DeWitt created a mathematical framework that blends quantum mechanics and general relativity. This equation contributes to our understanding of quantum gravity, a key challenge in merging gravity and quantum mechanics. However, the equation's main flaw is that it doesn't involve time, so it's not a complete unification, but it's the best we have so far. On the other hand, Heisenberg's uncertainty principle is more widely recognized. In simple terms, this principle states that you can't precisely know both the position and momentum of a tiny particle. Otherwise, you'd break some important physics rules. From this principle, we realize that empty space isn't truly empty. In the vacuum, particles can briefly pop in and out of existence due to random quantum fluctuations. This concept also relates to the idea of the false vacuum. So, how does all of this come together to help us? Dongshan explained it like this. We showed that once a tiny true vacuum bubble is formed, it has the potential to rapidly expand. The WIPM team describes these true vacuum bubbles as perfectly round spheres. They use this knowledge to determine how quickly the sphere's radius can grow. They go on to analyze the bubble in 3 possible space-time geometries: open, closed, or flat. Interestingly, they found that the bubble's expansion would lead to a Big Bang. This new equation provides fascinating insights into the universe. The theory proposes that dark energy, the force driving the universe's expansion, could be linked to a concept called quantum potential. Quantum potential is a component of the pilot wave theory, a less-known interpretation of quantum mechanics that offers an alternative or complement to our current understanding of quantum theory. Pilot wave theory aligns with existing quantum predictions, resolves paradoxes like Schrödinger's cat, and introduces the idea of quantum potential. One of the drawbacks of pilot wave theory has been its inability to make distinct predictions. All its predictions are either identical to the widely accepted quantum theory or are not testable. That's where the new derivation from WIPM enters the picture. With quantum potential being a key element of this new equation, scientists might revisit the pilot wave theory. This fresh perspective could potentially advance our understanding of the universe by providing unique insights that go beyond what conventional quantum theory offers. Imagine a scenario where our universe wasn't born from a traditional Big Bang, but from a colossal collision between 2 gigantic, unseen objects in a higher dimensional realm. This is the essence of the ekpyrotic universe theory. In this theory, our universe isn't just the familiar 3 dimensions of space and 1 of time. Instead, it's a 4-dimensional brain that exists within a higher dimensional space. Think of this brain as a sort of cosmic sheet, floating in a larger reality that we can't directly perceive. The name ekpyrotic comes from ancient Greek, referring to a fiery, cataclysmic event. Just as a collision between 2 vehicles can create a massive release of energy, the collision of 2 brains in the higher dimensional space generates a burst of energy and matter that gives birth to our universe. This collision is like a spark that ignites the expansion and evolution of everything we see around us. This theory offers an intriguing alternative to the popular inflationary model of the universe's birth. The inflation theory suggests that the universe underwent a rapid expansion phase, driven by a mysterious field. But in the ekpyrotic scenario, it's not just the expansion, it's the result of a dynamic interaction between these higher dimensional brains. This concept doesn't just change how we think about the universe's beginning, it also introduces the idea of cyclical patterns. The ekpyrotic universe theory proposes that this collision isn't a one-time event. Instead, it suggests that our universe could be just one cycle in an ongoing series of collisions and expansions, with each cycle potentially leading to the birth of a new universe. Maybe the universe is a result of a colossal cosmic experiment conducted by an advanced civilization in a higher dimension. They created our universe as a simulation to study the emergence of life, matter, and fundamental forces. Maybe the universe is a mesmerizing projection that emanates from a higher dimensional realm, a concept that leads us to contemplate the profound idea that our reality is but a holographic reflection of an immensely intricate and multifaceted existence. Maybe the universe is a self-aware entity, a cosmic consciousness that came into being to experience existence in its myriad forms. This universe consciousness evolves through galaxies, stars, and living beings, accumulating knowledge and understanding along the way, like a universal self-discovery journey. Maybe space is like a phoenix in an eternal cycle of life and death. Maybe time repeats itself in an infinite recurrence of the universe after universe. Or perhaps this is the only universe after all, with a small hot beginning and a cold, dark finale, until the day comes when we discover how to extract more information from the universe than presently seems possible. We have no choice but to face our ignorance. The Big Bang still happened a very long time ago, but it wasn't the beginning we once supposed it to be. Imagine if we went back to when our solar system first formed and replayed that moment a billion times. It's very unlikely that humans would appear even once in those scenarios. But if we look back to the early stages of the hot Big Bang, a universe filled with stars, galaxies, planets like Earth, and countless opportunities for life to emerge becomes almost certain. This is because the rules and basic stuff of the universe stay the same. A universe born with certain materials will create specific elements. One with unevenness in density will make the first stars. The presence of dark matter will lead to stars with heavy components. When there's a second generation of stars, it results in planets like Earth and stars like our Sun. And when you have Earth-like planets, the possibility for life to thrive for a very long time appears. The rest might be influenced by randomness, but that's what allowed us to come into existence. It's now our responsibility to make the most of it. This video would not be complete without delving into the philosophical side of the topic. While we have already explored scientific and cosmological perspectives on the origins of the universe, it is essential to consider the philosophical arguments that have shaped our understanding of how something could emerge from nothingness. When contemplating the philosophical question of how the universe came from nothing, various arguments and theories have been put forth throughout history. These perspectives offer insights into the nature of existence, causality, and the very fabric of reality itself. One influential philosophical argument is rooted in classical metaphysics, where the principle of ex nihilo nihil fit is often invoked. This Latin phrase translates to "out of nothing, nothing comes." Philosophers who adhere to this principle, such as Parmenides of Elea, question the very possibility of something emerging from absolute nothingness. They challenge us to consider alternative explanations or underlying principles that could account for the existence of the universe. Another prominent philosopher who contributed to this discourse is Gottfried Wilhelm Leibniz. Leibniz pondered the question of why there is something rather than nothing, and he proposed the principle of sufficient reason. According to Leibniz, everything that exists must have a sufficient reason or explanation for its existence. This principle invites us to search for a deeper underlying cause or rationale behind the emergence of the universe. These philosophical arguments highlight the profound metaphysical implications of the universe coming from nothing. They encourage us to critically analyze our assumptions, question the nature of causality and existence, and explore alternative explanations beyond scientific and cosmological frameworks. By considering the philosophical dimension of the topic, we gain a broader perspective that goes beyond empirical evidence and scientific theories. It prompts us to engage in deeper reflections on the fundamental nature of reality and existence itself. And there you have it, a thought-provoking exploration of the origin of the universe and its fine-tuned nature. We have ventured through scientific, philosophical, and metaphysical perspectives to delve into the mystery of how the universe could have emerged from nothingness. Philosophy has enriched our understanding by introducing arguments such as the teleological perspective, which suggests an intelligent designer or grand cosmic plan, and existentialist philosophies which explore the subjective meaning we create in a seemingly indifferent universe. These philosophical insights remind us of the broader implications and existential significance of our inquiries. Furthermore, we have contemplated the probabilistic and deterministic nature of the universe, recognizing the interplay between chance and order, and the ongoing pursuit of a unified theory that can reconcile these seemingly divergent perspectives. Throughout our exploration, one thing becomes clear. Our quest for understanding the origin of the universe is far from complete. The more we uncover, the deeper the mysteries become. The notion that the entire universe came from nothing challenges our intuition and invites us to contemplate the fundamental nature of reality itself. As we continue to seek answers, it is important to remain open-minded and embrace the awe-inspiring complexity of the universe. Whether through scientific inquiry, philosophical contemplation, or the integration of diverse perspectives, we are driven by an insatiable curiosity to unravel the secrets of our cosmic origins. Hopefully, by nurturing our collective curiosity, fostering interdisciplinary collaborations, and nurturing a sense of wonder, we will inch closer to unlocking the enigmas of existence. As we traverse the uncharted territories of knowledge, let us embrace the grandeur of the questions that lie before us. Thanks for watching today's video, and I'll see you in the next one.